Now, what if you have more than one partially filled subshell? For example, helium excited state 1s1, 2s1. That gives you 4 Slater determinants. What are those 4 Slater determinants? You can have 1s, 1s bar, 2s, 2s bar. You can have this, that, right? They can both be spin up in the 1s. The other electron is also spin up in the 2s. Or it can be spin up in the 1s, spin down in the 2s, right? So you can have 1s, 2s, spin up in the 1s, spin down in the 2s. What's the other possibility? It can be spin down in the 1s, and it can be spin up in the 2s. And the other possibility is spin down in the 1s, spin down in the 2s. Okay? What are the possible m sub l's and m sub s for this? S orbitals, what's the quantum number L? 0. So m sub l can only be 0. The only possible m sub l you can get here would be 0. What are your possible m sub s values? Okay. 1 and spin up for the first one. Spin up, m sub s is +1. For the second Slater determinant would be spin up, spin down, m sub s is 0. For the third one, spin down, -1. For the fourth one, I'm sorry, spin down, spin up, so this is 0. And then for the fourth one, they're both spin down, -1. So that tells you this +1, this -1, and one of the 2 linear combinations from this would be part of what? If your m sub s goes from +1, 0, -1, that would be a triplet, right? So you get a triplet state. 3 of those functions, 3. So actually, you're just going to have function 1, function 4, and one of the linear combinations you get from 2 and 3 will form a triplet. That's your triplet S term. Okay? And the other linear combination from 2 and 3 will give you the singlet S. Okay? So that's how you would derive your terms. In general, if you have 2 electrons in different subshells, you'll get a singlet term and a triplet term. Another way to look at that is that either both electrons are both spin up, okay? So they're both spin up or they're both spin down. That's part of the triplet. And the other one, you have 1 spin up, 1 spin down. You have 2 possible linear combinations of these. One of these linear combinations will be part of the triplet, and the other linear combination would be part of the singlet. Sometimes it's convenient to think of this as part of the triplet, and then the one where you have spin up, spin down, that's part of the that would be a singlet, would be one there where the 2 spins are completely opposite, so they end up with a 0 total spin. Okay. Whereas here, you sort of like have a spin, a net spin going that way. Okay. So in general, in these cases, okay, you can use the Clebsch-Gordon formula. Okay. Your total L will just be L1 plus L2 all the way down to absolute value of L1 minus L2. So for example, if you have 1s1, 2s1, what's our L1? S orbital, L is 0. What's our L2? 0. So you can go, your possible value of L goes from 0 all the way down to absolute value of 0 minus 0. So the only possible L you can get is 0. Okay? So that's an S term. And your total spin angular momentum would be S1 plus S2 all the way down to absolute value of S1 minus S2. What's our S1? any electron, S is 1/2, 1/2 plus 1/2, all the way down to 1/2 minus 1/2. And so that gives you 1. So that gives you S equals 1 or 0. And this is your triplet, right? 2S plus 1 is 3. And S equals 0 would be your singlet. Okay? So your helium 1s1, 2s1 will give you a singlet S and a triplet S. How about helium 1s1, 2p1? What would be your terms from that? L1 is 0, L2 is 1. Okay, so what are possible L's? L1 plus L2 all the way down to absolute value of L1 minus L2. So 0 plus 1 all the way down to absolute value of 0 minus 1. So that gives us 1, and that's it. 0 minus 1 is 1. Okay, so you can only get L equals 1. So what kind of term can you get here? You get a P term. Okay. And what kind of multiplicities can you get? Same thing, 2 electrons, so singlet and triplet. So you can get a singlet P and a triplet P. All right. Now, how many functions are associated with a singlet P? 1 times 3. That's 3. How many functions are associated with? So that's 3. How many functions are associated with a triplet P? 2s plus 1 times 2l plus 1, 3 times 3, that's 9. 3 plus 9, a total of 12 functions. That means for that configuration, you should have been able to write 12 Slater determinants. What are those 12 Slater determinants? Let's go back. One of the electrons is either in the 1s or the 1s bar, right? So there's 2 possibilities there. The other electron is either in the 2p plus 1 or 2p plus 1 bar or 2p0 or 2p0 bar or 2p negative 1 or 2p negative 1 bar. So that's 1, 2, 3, 4, 5, 6 possibilities. So 2 ways this can happen times 6 ways this can happen. You can get 12 possible Slater determinants. So you could have just tabulated this, put up all your M sub L's and M sub S, and work out the term symbols. But it's just quicker to just use the Clebsch-Gordon formula. You can see you get your singlet P and your triplet P. Okay, so that's 3 plus 9, that's 12. So you could have worked it out the way we did earlier, but it's quicker if they're in separate subshells. You know, then you don't have to worry about Pauli's principle, because they can be they can both be spin up, both spin down, or so. And since you're tabulating it with using spin orbitals anyway, it doesn't matter. But this is just a quicker way of doing it.